So until now we have been talking about the surface energy between two phases and the curvature of an interface between two phases. Now we're going to look what happens if we have a contact line between three phases. So the simplest system is, for example, I have a solid surface on top of which I put a liquid droplet. So draw that liquid droplet. So, and then I have solid, liquid, gas. And now I have three different type of interfaces. I have a solid gas interface, a solid liquid interface, and a liquid gas interface. And I have something that is called the triple interface line, which is the point where the three phases come together. And basically, if this is a spherical droplet, then this interface, of course, is the circle that goes around here. So these are 2 points on the circular triple interface line. How does such a system, what is the equilibrium state for such a system? Well, I have three surface energies. So if this is a system where the surface energy is dominating, such as in a microscale, what will happen is that the total surface energy of the system, UT, equals surface energy of the liquid gas system times the area of the liquid gas system, so that's this area, plus surface energy of the solid liquid interface times the area of the solid liquid interface, plus the surface energy of the gas solid interface, so the solid gas interface times the area of the solid gas interface. So the sum of these tell me that is the total interfacial energy in the system, and that energy will typically try to minimize itself in the system. Yeah, so system always strives to its minimum energy, and it will do that by assuming a certain shape. And very typically I will find, so if I look now at the force that are at stake, so I see first of all the liquid gas interface has an energy, that's this one here, the curved one. It tries to minimize itself, so if I look at the point here on this triple interface line, I will see that it will be this. There will be a force that is not perpendicular, it's more like in this direction, tangential to this. So this is this gamma liquid times, so there's a force trying to minimize this circular area here. It has, of course, this direction. Then I have a solid liquid interface. This is this one, so I will have a force that always also tries to minimize this direction. And then I have a solid gas, so I have a force that tries to minimize the dry area. And it will actually be a little bit larger in this case. And this system is at equilibrium if the sum of these forces equals 0. There's also, of course, a force down here, but I'm not going to draw that. I'm only going to consider now, for simplicity, the forces in the horizontal direction. So I see that in the horizontal direction, I have this force plus there's an angle theta here, and if I project this vector here, I get this vector. So the sum of these two, the projection of this one plus this one, must equal this vector. Yeah, I have to have force equilibrium in the plane. Then my system is in equilibrium. So I can say that, how do I write that? I can write that, that means that gamma solid gas must equal gamma solid liquid plus the projection of gamma liquid gas. But it's projected, so I have to do times cosinus of the angle theta here. So if this system is in equilibrium, it means I will have an equilibrium angle theta here, and this is what I call the contact angle. So any liquid, gas, solid system has an equilibrium contact angle theta. And this formula I call actually I call Young's equation. So I will now see there's two. I can have basically my universe I can divide in two different type of systems. I can divide in systems where this cosine theta here, where this angle is smaller than 90 degrees, and systems where I have an angle where it's larger than 90 degrees. So any liquid-solid interface or liquid-solid gas interface, well, first of all, let's look at what is actually the influence of the gas. The interfacial energy of the solid to the gas and of the liquid to the gas will be mainly determined by the properties of the liquid, of the solid, respectively of the liquid. Because a gas actually is more or less a vacuum with here and there so an atom moving. It's basically empty space with here and there an atom very far. So there's very little atomic interaction of the atoms in the gas with the liquid or the atoms of the gas with the solid. So it's mainly what's actually the interaction within the solid or within the liquid that will determine these interfacial energies. So that's the first. So if I have such a system in air, or I put it in hydrogen gas or in helium or in any gas, more or less I will find more or less the same contact angle. And so now, as we said, there's two types of systems. There's systems where a small contact angle below 90 and one with a higher contact angle, higher than 90. And the ones with lower than 90 degrees, there I say that the liquid likes the solid. It likes to wet the solid. And I call such a system hydrophilic. It comes from Greek. Hydro means water and philic means like. So water liking. So a theta angle here, contact angle, that is below 90 degrees is a hydrophilic system. And if I have a solid liquid where this angle is above 90 degrees, I will call it hydrophobic. Phobos means fear in Greek. So water fearing, so water repellent surface. And you can see two examples of such pictures. Yeah, hydrophilic liquid is typically water on glass. Can have a very, very low angle, say 20 degrees or something. And here you see a picture on the bottom where you see water on Teflon. Teflon is, for example, a hydrophobic surface, or for example, the surface of your car after you wax it. So waxing a car is actually making the surface hydrophobic, so that liquid droplets kind of bounce off or don't want to stick on the surface. Yeah. And these are very important distinguish. So a surface is either hydrophilic or hydrophobic. And we see that has a large influence on the behavior of capillary filling, which is the next thing we're going to look at. So we're going to do a little experiment here. I hope you can see this. This is I petri dish with a little bit of red candy dye. And I have two sets. So I have small, so you can see small capillaries and large capillaries. And so let's first see what happens if I put a capillary into the liquid. I put it just in this angle. So I put it here, and you see what's happening. The capillary sucks up the liquid. It keeps on doing that until it will reach a certain height, or certain height in this case. So in this case, it's a glass capillary. Glass is very hydrophilic. So the liquid solid surface, the glass surface, likes to be wetted, and it minimizes energy by wetting. So that's what it's going to do, and in that way it's going to create a column of a red color dye, and it's going to keep on wetting until the gravitational force counteracts the capillary force, and you come to some kind of equilibrium. I don't know, you can't really see this side, but let me try to put this straight. Let's see if you see. So I try to put this entirely horizontal now, so you get an idea of so. The capillary height is about a centimeter in this case.